take it away. So Bogdan's going to tell us about NMR capabilities in Kyiv. Please go ahead.
So, hello everyone. Let's get it started. Here is one of the most beautiful and biggest cities in the world. It's the capital of Ukraine, Kyiv, which is one of the most recognizable building, most recognizable sites, and right in the heart of the city. It's located below the letter K on the map. This is the gorgeous red main building of Tarasovchenko National University of Kyiv, and the chemistry department on the right from it, highlighted in the red frame. In general, possibilities for chemists located in Kyiv are very extensive. They are very diverse in different institutions, universities, companies, and so on. As chemists, we are highly versatile in available techniques, methods, equipment, facilities, and the other example is Chem Biocenter, which is a scientific division of the Kyiv National University that performs 4-class research in organic synthesis and medicinal chemistry, and it's located on the left bank of Kyiv. So Chem Biocenter uses capacities of private company NMR, which is highlighted with a blue arrow. Yeah. And this is the place where an enormous ratio of amazing things is going on. And NMR is a very important company for chemists in Ukraine, and one of the key figures in organic synthesis in the whole world. The whole blue frame represents the building of companies. Actually, there are nearly 10 more new buildings around, but now we are unable to make a new aerial photo with the drones, since presumably it will be taken down by anti-aircraft warfare very fast. There are other related institutions. However, my presentation is limited in time, therefore it includes only places where I am directly related to. So first, let us talk about where it happens. First, the organic chemistry department was founded over 130 years ago, and notably the first head of the department was Professor Reformatsky, which is a well-known organic chemist who is responsible for introduction of organometallic compounds to the scientific community. My presentation is about NMR spectroscopy, the most essential method for organic chemistry, and we have NMR laboratory in chemistry department bearing a spectrometer with a working frequency of 400 MHz. Students and staff are able to perform routine experiments and analysis of products and their scientific results and practice labs upon general course. The first important question about is the studying process. Organic chemistry and NMR spectroscopy are two main courses which I directly participate in. In particular, the NMR course includes key topics of NMR experiments and properties of the resulting spectra. Starting from all features of magnetic nuclei and NMR phenomena through some key aspects of homo and heteronuclear experiments, all the factors that influence chemical shifts, shieldings, direct, short, and long range spin-spin couplings, and the overall shape of signals, everything. The second part is devoted to practical problems, predictions of NMR spectra, and solving the combined sets of problems containing NMR, mass, and infrared spectra. The last part includes working with NMR software to analyze and describe correctly raw spectral data. Good theoretical and practical background of our students is really highly demanded. Initially by me, my students know that very well. This is required in scientific work, employment, and further career steps, not only in our institutions, but companies all around the world. And highly qualified chemists are what we are aimed for in our studying programs. Simultaneously, scientific research is traditionally done in different spheres, and it's really crucial part for teaching process. And therefore, our students actively participate in the research programs. At the end of their studies, students present their scientific results obtained by them under some supervision of professor or PhD students. Our professors and researchers of the department collaborate with many leading scientific centers, private research companies in Ukraine and abroad. And our students have a lot of possibilities with these connections. And here's one of the most prominent examples. As I mentioned before, organic chemistry department collaborates really closely with Chem Bio Center and INAMIN. INAMIN was founded over 30 years ago and became one of most significant company in organic synthesis. Someone could ask you, like, is this company like really that strong and powerful and important? And the answer is definitely yes. As scientists, let us talk about some numbers and values. Today, the company provides access to the world's most extensive compound catalog and tangible collections, like nearly a half, I believe, of the world building blocks and reagents, and a variety of chemical and biological services. The largest collections of around 300,000 building blocks and 4 million commercial screening compounds is available, and a recently updated library of 36 billion readily accessible compounds could be synthesized by INAMIN. Expectedly, in order to operate such large libraries of compound, INAMIN has a well-organized and high-throughput analytical department. There are more than 60 preparative HPLC chromatographs, which could provide over 2,000 pure compounds daily. And what about NMR spectrometers? There are already 5 devices. One is being prepared for launch. So the NMR laboratory could provide about 5,000 spectra per day. So here is Andrzej Kozicki, my colleague and co-author of a series of papers, who pointed at one of the devices, particularly one of the main workhorses for our routine NMR experiments. Actually, this is one of my recent classes, which is shown in this photo. There is even my reflection could be seen on the surface of the spectrometer. And Andrzej showed the actual NMR experiment and provided notable comments and some understandable pieces of advice for bachelor students. And the skillfulness of young chemists, I believe, has improved dramatically thanks to Andrzej. Obviously, a lot of key practical aspects should be clarified for students for a better understanding of the experiment. And the main part of spectrometers were shown, as well as the setup of NMR software, including the number of scans, trimming, deuterium logs, etc. For example, here is a discussion on sample preparation to obtain good NMR spectra. Like the best experience is, like the bad experience is the best one, at least the most memorable one. So there was a bunch of representative and sometimes funny stories on samples with a gradient of concentrations. Like if we look closely at the NMR tube, we can even observe it. Some precipitates from solvent that of note, samples with occurring site reactions, some good smelling materials, and so on. So, and the best way to show difference is the experiment with some visible results. Here is the resulting NMR spectra of the homogeneous solution and some unmixed solution with the gradient of concentration. Gradient of concentration along the NMR tube results in broadening, signal distortion, some extra peaks, and overall wrong spectral. Bubbles are another enemy which provides some non-homogeneity and enhanced relaxation and NMR spectra of lower quality. Another great tool which was discussed is discussed for improvement of the quality of some NMR data is changing solvent from, for example, dimethyl sulfoxide to deuterochloroform and vice versa. And this is especially the case when rotary is a real problem, where a bunch of better resolution could be attained by use of, for example, dimethyl sulfoxide instead of deuterochloroform. Like even in these days of in these days of high field NMR, it often happens that protein spectra show either an overlap of signals or higher order effects because of small chemical shift differences. And in this case, a sample change of solvent or addition of aromatic solvent could dramatically simplify the spectrum with a better resolved signals. Inter and intramolecular proton exchange could be an additional real problems for heterocyclic aromatic compounds that has plenty of exchangeable acidic protons, for example. And it often broadens almost all signals, even of the nearest CH groups, which makes the acquisition of the spectrum difficult or sometimes even impossible. especially in the case of two-dimensional HMPC experiment, which will be discussed a little bit later. However, the addition of, for example, trifluoroacetic acid is a good life hack that made possible to get a good spectra faster and possible. And finally, the actual NMR experiment, which takes about 13 seconds for the skillful operator who can provide over 1,000 spectra per one shift. So now let's change the subject from teaching and visiting labs to our research, yes, and aspect that could be solved by our NMR lab. So aside from custom synthesis and stocking compounds, we have a great range of various research projects that can be represented in various European and American chemical journals. All types of works included a lot of NMR experiments at every step, starting from the analysis of the reaction mixtures up to the purity of products, up to study of relative configurations like cis and trans isomerism, and analysis of stock libraries of compounds after the prolonged storage. The key works of our scientific groups, our main goals and key results are partially disclosed in several articles published in a special issue of the European Journal of Organic Chemistry, which was dedicated to enamine in 2021. And this slide represents some selected examples of molecules from our recent papers. And imagine that you are working with these novel molecules and want to publish them in some prestigious European or American journal. What NMR spectra should be recorded prior to the submission of the manuscript? We perform easily a full set of basic sensitive NMR experiments which are required for both novel and known compounds, especially prior to the publication, to illustrate all the spectral characteristics and purity of compounds. Everything looks beautifully simple and clear in the case of some heteroaromatic building blocks presented on this slide, for example. The presence of magnetic fluorine atoms provide multiple structure signals of 1H and 13th carbon NMR with clearly visible mono, di, and trifluoromethyl substituents, which is additionally conferred with a very specific regions on 19th fluorine NMR. More interesting spin-spin coupling system could be observed in a recently published, for example, dimethyl phosphine oxide bearing on the sulfonyl fluoride groups. But what could you have noticed in this desubstituted cyclobutanes in the presence is the presence of asymmetric centers. This is really important to confirm the structure and relative configurations of the substituents of all compounds prior to the publication or stocking. You should provide all the evidences that you are dealing with, for example, trans isomer and not its cis counterpart. A series of two-dimensional NMR experiments and nuclear overhauser effect studies are commonly used to assign all signals of the corresponding atoms of the molecules proposed, as well as their spatial locations. These experiments are suitable for study of, for example, complex diastereomeric mixtures by stepwise analysis of all spin systems. For example, we have a photochemical 2+2 cycle addition reactions of alkenyl boronase and maleimides, which resulted in exo and endo cycloadducts. However, in the case of beta monosubstituted alkenyl boronase, two more products are formed, each exo and endo cycloadduct with relative cis and trans configuration. The structure of the products could be established by a series of NMR experiments, but why do we need them? Not only to find structure of the major product and overall diester selectivity of the reaction, but also some mechanistics inside of these reactions. And here are the selected examples of molecules studied by a series of two-dimensional NMR and some NOVI experiments. Major products of the cycle addition reactions are shown in this case, and to be honest, this analysis is quite challenging and time-consuming and requires a lot of attention in the stepwise analysis and finding all correlations between all bonds and through space correlations. These problems could be considered as putting together like a middle-level to three-dimensional puzzle with several layers. And typical structural study includes a set of COSY and HQC experiment. These two steps allowed for an assignment of hydrogen with carbons, while the further relative localizations of hydrogen in space could be performed by 1- and 2-dimensional NOI experiments. A series of NMR experiments with different cycloids could be used to provide the statement that, for example, 1,3-dipolar 3+2 cycloaddition of alkenyl boronides proceeded in a diester selective manner to give cis and trans substituted borylated pyrrolidines with the relative stereochemistry of the starting alkenes. So another example of this diester selective reaction is the intermolecular nucleophilic substitution of cyclopentane carboxylate, which resulted in isomeric Hausans. Again, the three-step assignment by COSY, HSQC, and NOI is enough to evaluate the relative configuration of substituent. Two-dimensional NMR experiments are not always required, obviously, for the correct analysis of molecular structure. Sometimes thoughtful analysis, like about a molecular symmetry and spatial locations of all atoms, is enough for the possible different. It's enough to predict all the possible differences in spectral data. For example, cis and trans isomers of azepine 4 and 5 diol could be distinguished only by the common one-dimensional 1H NMR experiment. Symmetric molecules are quite common, and it's fascinating how constitutionally the same molecule with different relative positions of the same substituents could dramatically change the spectral properties. And for example, on uniform sampling is acquisition method of NMR experiment with 2 or more dimensions. With NUS, only a subset of usual linear sample data is recorded. For example, 25% or 50%, while reconstruction algorithms are used to get a correct spectrum from such a sparse dataset. And it's a great method to increase the resolution of two-dimensional NMR spectroscopy at the same time. The other challenging problems in our study is substitution patterns and the constitution of defined regioisomer among structurally and chemically related analogs. For example, several common pathways could be elaborated in the case of pyrazoles bearing substituent and certain fifth position, including NOI and various HMBC experiments. Heteronuclear experiments could be performed either at carbon atoms or nitrogen atoms, and so on. And for example, the synthesis of fused pyridine carboxylase from our work by reaction of beta-alkoxyphenyl dioxylase with amino heterocyclic depends on the R1 and R2 substituents of the CCC biselectrophile. And the resulting is, this results in alpha or gamma substituted pyridine carboxylase. And their structure could be established by a series of two-dimensional NMR experiments followed by some NOI correlations. So this sequence of experiments could be adapted to various organic molecules, even some microcyclic derivatives with some representative NMR experiments shown in this slide. Our other opportunity is some monitoring reaction, and the main reaction in this case starts when the temperature reaches like 0 degrees. This is the first phase, proceeded very quickly and finished in nearly 10 minutes, which could be monitored by NMR experiments by precise analysis of chemical shifts of various species that are formed, including some 4 and 5 coordinated silicon-containing species. So, summarizing, we are able to do a series of routine NMR experiments, one-dimensional, two-dimensional experiments, in order to evaluate all the properties of spectral properties of our molecules in our works. So I would like to give some special thanks to people who keep the ball rolling, and this is Andrei Kozitsky. So thank you very much for some fruitful discussions and performing challenging experiments with product from our research programs. And Alexander Grigorenko, who taught me NMR experiment in 2016 and many other subjects later. And thank you very much for attention. If you have some questions, I would be very happy to answer them. Yeah.
Superb. Thank you very much indeed, Bogdan. That was a beautiful presentation, very authoritative, and it was great to see what's going on in Kyiv. Again, can I just remind people, if you didn't, maybe just put questions into the chat, just so that we can keep going with the schedule, because we've got a long day. But Bogdan, thank you very much indeed. Super talk. Okay, so let's move on.